Okay, this is going to be our first video on our module on rotational motion here. And so we're going to start off by talking about angular acceleration, but even before I start talking about angular acceleration, I'm just going to point out that there's a lot of concepts in this module. So in the last module, we talked about torques and we talked about statics, right? And so really in the last module we were only interested in two of the topics in the chapters in the text. That's kind of in stark contrast to this chapter, which is full of useful ideas. In this chapter we're going to talk about maybe a half dozen or even more ideas that are going to be useful, that we can generate interesting tools to solve problems with in physics, right? So again, last chapter we only introduced the definition of torque and this idea of static equilibrium. Really, we just had to recycle our old idea of not having any net forces, sort of reusing Newton's second law, and then imposing that we have no net torque, right? But now here we're going to introduce angular acceleration in this first video, but I'm thinking that we're going to see at least somewhere between 6 and 8 videos in this module, and we're kind of going to go over a whole bunch of different topics that we talked about in a linear context and expand them now into ideas in a sort of rotational context. Okay, so we're going to take a look at some of those as we go, but I just wanted to mention that this is probably going to be a little bit of a longer module, and we'll probably see some more videos here than we did in the last one. Okay, so let's start off with angular acceleration, and to do that we're going to begin with just a quick review, or just reminding ourselves really of what our definition for angular velocity was, right? So back when we talked about uniform circular motion in our fifth module, we talked about this idea of angular velocity, right? And so I've rewritten it here. We have our idea, our definition of angular velocity, and it's defined as the change in angle over the change in time, right? We also saw there that we can relate our angular velocity to our tangential velocity, or our linear velocity, through either one of these equations. We can write our linear velocity is equal to our radius times our angular velocity, or rearrange it and get the other equation, right? So this is useful. Now we're going to continue to sort of work with this idea, and now we're going to define this idea of an angular acceleration. So we had an angular velocity, which we could sort of understand in analogy to the linear idea of velocity. And now we're going to define an angular acceleration, which we do right here. So angular acceleration is the timed rate of change of our angular velocity. So it's a change in our angular velocity over the change in time. And so really normally we would think of this as a vector quantity, right? So angular acceleration would be a vector and angular velocity would be a vector. But we can also use it written this way, like scalars. And I'll just point out now that the SI units for our angular acceleration are radians per second squared, which is not surprising, because if we think back, we remember that our angular velocity had units of radians per second. So this is just radians per second, so radians per second squared. And so this is I should have probably boxed this. This is a definition we're going to want to remember. Okay, I'll get rid of this for the notes, and we can move on. I'm going to jump right into an example of sort of how we might use this. That'll probably be the easiest way to start getting a handle on this. I have the numbers worked out here on a piece of paper, but let's read through it first. So we want to consider a bike which is placed upside down, with the bike wheels sort of facing upwards, so you can just spin them sort of freely, right? So we're imagining this bike upside down, and we can spin the wheels. The wheel starts from rest, and then it experiences an angular acceleration resulting in an angular velocity of 250 RPM in 5 seconds, okay? And so we want to calculate the angular acceleration. And so So what do we have? Well, what do we know? We can start off by writing down that we know that our change in our angular velocity is going to be equal to well, a positive 250 revolutions per minute, right? Like our RPM, right? But we need this in terms of radians per second, so that we're working in SI units. So let's get this into the sort of correct units that we want, so into radians per second. We know that there are going to be 2 pi radians in every revolution. And then we also know that there's going to be, well, in 1 minute, there's going to be 60 seconds, right? So if we multiply through by this, multiply through by the units, we're going to see that our change in angular velocity is actually equal to, if you sort of feed this into a calculator, you'll see that it ends up being equal to 26.2. Let me fix that. 26.2 radians per second. Okay? And so now that we have this in terms of radians per second, well, we can just use our new definition. We know that our angular acceleration is defined as our change in angular velocity over the change in time. We just calculated what that change in angular velocity is. That's 26.2 over the change in time. Well, we're told that's 5 seconds. And if you do that calculation, you're going to find that you get a 5.24 radians per second squared angular acceleration, right? And so that would be the answer to part A. Okay, so for part B, what are we looking for? So the wheel gets up to speed here, and then if the wheel brakes with an angular acceleration of A equals minus 87.3 radians per second squared, how long will it take for the wheel to stop? Right? So we want to solve for delta t, and the easiest way to do that is, well, we just take our definition that we just generated, but now we're going to solve for delta t, so we can see that delta t is going to be equal to delta omega over alpha. And we just solved for what our delta omega is in terms of radians per second. But let's remember that we went from 0 to 26.2 radians per second in 5 seconds in the first part. But now we're slowing down from 26.2 radians per second down to 0 radians per second, and so this is going to be a negative 26.2 over our alpha. Well, we're told that alpha is negative 87.3 radians per second squared, and so if we do the calculation here, feed this into a calculator, we're going to end up finding that our change in time, our delta t, is equal to about 0.3 seconds. Okay, so it's going to take us 0.3 seconds to slow down from 26.2 radians per second down to 0 radians per second if we apply this negative angular acceleration of negative 87.3 radians per second squared. Okay, and so that little example just sort of demonstrates sort of a very simple way to think about this this new concept, this angular acceleration. Okay. And so now we want to think about tangential acceleration also. So in our work on uniform circular motion, we saw that angular velocity and tangential velocity were related through this expression that I've put here, right? And so now we want to do the same for linear or tangential acceleration, and our angular acceleration, right? So we're going to start off with a simple definition from kinematics. So we should remember from kinematics that our linear acceleration is defined as a change in velocity over the change in time, as we see here. But we also have this idea from our earlier work in uniform circular motion that our linear velocity is equal to the radius times our angular velocity, right? So let's substitute that in. So we're going to substitute this v into here, If we do that, we end up with this expression that I've written down here. Except I probably should have put a bracket in here, because really we're talking about the change in the quantity r times w, or not w, omega. Sorry. So the change in r times omega, except that r doesn't change, right? R is just a fixed radius for these types of problems. We can deal with situations where r is changing, but that'd be a much more complicated problem, not something we're going to be dealing with here right now. And so since r doesn't change, we can factor out the r. Then we have delta omega over delta t, remaining with an r out front, right? But we just said the delta omega over delta t, well, that is the angular acceleration that we just introduced, right? And so we find that linear acceleration relates to angular acceleration through a equals r alpha, okay? And maybe I should have mentioned that, but this symbol that I'm using here, this is the Greek letter alpha, which we use to signify angular acceleration, okay? And again, this is an omega, Greek letter omega, that's a lowercase omega. Okay, and so we've just sort of written down the analogous sort of equation to what we had in the case of linear and angular velocities, but now in terms of linear and angular accelerations, right? So we can write our linear acceleration equals our radius times our angular acceleration, or if we want, we can reorganize it obviously into this form here, okay? We'll do one more quick example for this video, sort of just demonstrating this idea. And I think I also have numbers for this. I do. Okay. So a motorcycle accelerates from 0 to 30 meters per second in 4.2 seconds. And we want to know what the angular acceleration of its 0.32 meter radius wheels are. Okay. And so, well, let's start off here. So we're told that the acceleration that this motorcycle is experiencing is going to be equal. Well, I mean, we know it's going to be the change in velocity over the change in time, right? But we're told that the change in velocity is 30 meters per second, and the change in time is 4.2 seconds. And so if we do that calculation, we can see that our linear acceleration is going to be 7.14 meters per second squared. Okay. And this, I'll just rewrite it here. This is our linear acceleration. Okay, so we have a linear acceleration, but we want our angular acceleration. So we want alpha. We know that we can write alpha from our equations up above here. We know we can write it as a over r. And so we simply just have to substitute in, these numbers, the radius which we're given in the question. And if we do that calculation, we're going to find an angular acceleration of 22.3 radians per second squared. Okay, and that would be the angular acceleration of the tires, or wheels, I should say, given this acceleration from 0 to 30 meters per second in 4.2 seconds. Okay, and so that kind of shows this new idea of angular acceleration and how it relates to linear acceleration. And so I've taken this table from the textbook here, and what we've really done now is we've developed sort of three connections from these ideas in linear calculations that we do to these ideas in rotational calculations. And this kind of just really nicely sums it up. So I thought I'd put the table in here. And so if we think about this, when we talk about rotation angle theta, angular velocity omega, and angular acceleration alpha, and then we think about sort of translation or linear distance, so that'll be x, right? Our linear velocity and our linear acceleration, we can just write down all these relationships, right? So these are three very useful relationships that we're going to use over and over here. I'm not sure why they kind of really want to put a sub t on these a's often, right? So you'll sometimes see the linear acceleration written like this, But when it's written, when you're writing the linear acceleration in the context of a rotational problem, people will often say a sub t. So it's like the tangential acceleration, but I'm just going to use a. You may see sub t in the text sometimes, but don't worry too much about that. So we're going to use these a bunch. We're also going to see them obviously rearranged. So it'll be something like this, right? But easily we can sort of shift these around to however we kind of want to use them, right? Okay. And so those are the three equations. We're going to work with these a lot more, but that'll do it for this video, and we'll pick it up with a new topic in the next one.